All right, so let's get started here. So I know that this is a very sad day here today because this is the last day of new content in this course. At the end of today, we won't have anything new to be learning. So I know it's very disappointing. Everybody contain yourselves here, all right? But we're wrapping things up and getting to the finish line. Let's discuss what these next few lecture periods are going to look like. So first of all, as we said today, we're going to be finishing up that thermodynamics lecture. So then on Friday, we will be doing our review session for Unit 4. All right? And that will be in preparation for next week. Y'all have your exam 4 on Monday the 5th, right? The 6th. Cool. That's how math works. Monday the 6th. And Tuesday the 7th. All right, so on Monday and Tuesday of next week, you will be taking your exam 4 in the testing center. So then in lecture on Monday, that will be our optional review session. I will not be taking attendance, but we will be going through review material, just going as many practice problems as we can do in those 50 minutes time period. So then on Wednesday of next week, we're not going to be having lecture on Wednesday of next week. As an adjunct faculty member, I am not on campus during those consultation days at the end of the week. So instead, I'm going to open up Wednesday's lecture period as my consultation day for this course. So y'all don't have to come if you don't want to, but I will be in here to answer any sort of course or content questions for you. All right, so again, Wednesday, no lecture. All right. Instead, there will be those office hours or consultation days. And again, I'll hold it in this room here. All right? That makes sense? Cool. All right. So let's finish this up here. Now we're going to roll everything that we've been talking about into this chapter all together here, reaching back to our first initial discussion of calorimetry, but then tying it into what we learned about reactions and reaction enthalpy. All right? So this reaction calorimetry, this is going to be a way to measure enthalpy changes in a chemical reaction. Right? We talked about how given that balanced chemical equation, we got a few different methods that we can use to figure out what our reaction enthalpy is. Well, how the heck did they get those numbers in the first place? How does one go in there and measure the enthalpy of a reaction? All right, and so it's going to use that calorimetry. So let's review real quick our calorimetry. This was how we measured heat exchange. And it all revolved around this formula, where the amount of heat that was absorbed or released by a material was equal to that constant value, we called the specific heat capacity, times the amount or the mass of the substance that you have, and then that observed change in temperature, right? So that change in temperature is the key there. How do you measure the enthalpy of a change of a reaction? You perform your reaction and you measure the change in temperature that's associated with that reaction, right? These reactions are releasing or absorbing heat. Well, that's going to change the temperature of that environment that that reaction is taking place in. If we measure that temperature change, we can figure out the amount of energy that was being released by that reaction. All right, so again, tying in what we did to calorimetry and now our reaction enthalpy as well. All right, so first of all, remember we said that if something absorbed heat, what does that do to the temperature? I got a piece of copper in my hand, for example, and it absorbs a bunch of heat. What's going to happen to the temperature of that copper? It's going to increase, right? So if something absorbed heat, it increased in temperature. Right? And we talked about how cold isn't really a thing, but when something gets cold, it's because it loses heat or releases heat. That would lead to a decrease in temperature. All right, so that's what we discussed when we were talking about calorimetry. And then we went on to reactions, and we were talking about enthalpy. And this is the heat absorbed or released by a chemical reaction. All right, so when we were talking about enthalpy, now in the context of chemical reactions, that same idea, that same quantity of heat we're talking about, but this was specifically in the context of chemical reactions. And we had these fancy terms here. We said that a reaction was exothermic, meaning it what? Released or absorbed heat. Exothermic means that it releases heat. And then endothermic means that it absorbs heat. All right, so when we perform an exothermic reaction in the lab, a reaction that releases heat, this will increase the temperature of our reaction vessel. Whereas endothermic reactions, they decrease the temperature of our reaction vessel. So how did we square these two things away here? When we were talking about calorimetry, we said that absorbing heat would increase the temperature. But in the context of a chemical reaction that absorbs heat will actually decrease the temperature. It would feel colder in your hands, right? Whereas when we have a substance that releases heat, that substance gets colder. But a chemical reaction that releases heat, that would warm up our reaction vessel. So how do we square these two things away? All right? The important part here is when that chemical reaction releases heat, where does that heat go? It goes into all of the surroundings, including your hand, right? So this exothermic reaction is releasing heat, but you feel it warming up because you are then absorbing that heat that's released by that chemical reaction, all right? So there's this important conservation principle, conservation of energy, all right? The amount of heat that's absorbed or released by a reaction plus the heat of what we're going to call the surroundings. And your surroundings are everything outside of that chemical reaction. So our Q surroundings is the heat that's absorbed or released by our surroundings. And again, our surroundings is just everything except that reaction. All right, these two energies combined here have to be equal to 0. We can't make any new energy out of thin air. Energy can't disappear into thin air. It's got to go somewhere. This equation right here is saying that let's say that we have a reaction that releases heat. Then every bit of that heat, down to the joule, has to be absorbed by the surroundings. And likewise, if on the flip side you had a reaction that absorbed heat, well, where is that heat coming from? It has to be heat that was released from the surroundings. These two quantities together have to sum up to 0. All right? So let's use this equation in sort of the simplest problem we can here. Let's say we have a chemical reaction. And that chemical reaction releases .3 kilojoules of heat. How much energy, how much heat is absorbed or released by the surroundings? All right, so we're going to use this equation where our Q reaction plus its surroundings have to be equal to 0. Well, my Q reaction is that negative 40.3 kilojoules. So then what must my Q surrounding be? What would I add to negative 40.3 to get me to 0? Positive 40.3. Look, this equation is almost too easy that it like trips people up here. You're just going to flip the sign, right? These two things together have to be equal to 0. So that means that your Q surroundings is going to be positive 40.3 kilojoules. Right? Again, every amount of heat that's released by that chemical reaction has to go somewhere. It's going to go into your surroundings. All right? Was heat absorbed or released in this reaction here, or in this process here, by our surroundings specifically? My reaction released the heat, so what did the surroundings do? They absorbed that heat that was released by the reaction. Right? So in this case, it's absorbed, not released. And again, we can see that based on the sign of that value of Q. A positive Q means that we are absorbing heat here. So the temperature of my surroundings in this reaction would increase because my reaction has released heat. All right. So these particular types of problems work really well for a specific type of reaction, all right? A precipitation reaction. Really any solution reaction, but precipitation reactions are a good category for this here. All right, what we're going to do is we're going to perform our precipitation reactions. In what's called a calorimeter. And this is just a fancy way of saying an insulated vessel. And what it means to be insulated is that no heat is allowed in or out. All right. Many of us are walking around with some calorimeters right now. These insulated vessels that are used to prevent our water, for example, from heating up. Or if you put like hot coffee in there to prevent that heat from leaving that vessel, right? So a calorimeter is just a nice insulated vessel. It doesn't allow any heat in. It also doesn't allow any heat out, all right? So if we perform this reaction in our calorimeter, then our equation simplifies. We're no longer worried about all of our surroundings, all of the room and everything like that. We're only worried about what's contained in that calorimeter, which means that the Q of our reaction, every bit of heat released by our reaction, will then wind up in our solution. Those surrounding water molecules in that precipitation reaction. All right? We don't have to worry about the rest of the universe because we've carried out this reaction in a vessel that won't allow heat to be exchanged. Everything's going to be contained in that vessel there. All right? These calorimeters range from the coffee cup that I believe you all would have used in your 1AL lab to these fancy kind of tens of thousands of dollars instruments that they have that you can operate with the computer and stuff like that. They kind of range in how fancy they are, but the bottom line is the same here. They don't allow heat in or out, which means every amount of heat that's released by that reaction will be absorbed by the surrounding solution molecules, the surrounding water molecules. All right? All right, so let's do one of these from scratch here. We're going to look at a precipitation reaction. All right, we're going to look up the delta H of this reaction, but the first thing that we need to do is you need to convert it into its net ionic equation. All right, once we get our net ionic equation, we can look up our delta H values of this reaction. All right, so our net ionic equation here, we're going to get rid of everything that remains aqueous in this solution. So we're left with just our silver ions combining with those chloride ions to make that precipitate, that solid silver chloride. All right, and so for the sake of time, while y'all were working on that, I went to our constants page and I grabbed these values for this delta H of each of these compounds. So I'm going to list them below here, and y'all are going to calculate the delta H of this reaction. right, to get my delta H, I need to do my products minus my reactants. Right, the sum of my products minus the sum of my reactants. And I get a value of negative 65.7 kilojoules per mole. All right, so first we're going to get our net ionic equation, then we can look up that net ionic equation on our constants page to figure out our enthalpy of our reaction here. But this reaction enthalpy is the amount of heat that's released if 1 mole of reaction were to happen. We don't quite have a mole of reaction happenings. Let's say if 0.25 moles of those silver ions are consumed, how much heat is absorbed or released by the reaction? All right, this is the enthalpy stoichiometry that we learned how to do last class. All right, so from our balanced chemical equation, we can build these stoichiometric ratios. Our balanced chemical equation shows us how much of our reactant and product is in 1 mole of reaction. So we can build these stoichiometric ratios where I have 1 mole of my silver ion being consumed per mole reaction. Right? So these are these new stoichiometric ratios that we learned how to build last class. Not terribly crazy, right? Just the coefficients from our balanced chemical equation. So using that new stoichiometric ratio, we can start with our amount of silver ions, that 0.25 moles of silver. And then we can multiply by that stoichiometric ratio where 1 mole of silver is consumed per mole of reaction. All right, and why are we trying to convert to moles reaction? Because that's the units in our enthalpy here. This enthalpy value, the other thing we learned how to do is to take that negative 65.7 kilojoules per mole, and similar to what we did for our molar masses, in order to use it in our math, we're going to split those units up. This becomes negative 65.7 kilojoules in 1 mole of our reaction. All right, so that's how we take that enthalpy information and use it in our stoichiometry. We break up those units of kilojoules and moles. All right, so now I can multiply by that enthalpy, my mole reaction, negative 65.7 kilojoules of heat. All right, I punch that into my calculator, and I get negative 16.425. What are my units going to be? Kilojoules, right? We can see that it's all set up correctly because moles of silver ions cancel out. Moles of reaction cancel out, and I'm left with just kilojoules. All right, I'm going to mark these 2 sig figs with a bar. But we're going to go and do more math with this number. So am I going to round it? No. All right, cool. So we'll just keep it marked so we know how many sig figs there are. All right, so now we figured out how much heat was absorbed or released by a reaction. First of all, was it absorbed or was it released? It was released, right? Cool. So So now we need to figure out how much heat was absorbed or released by that solution. All right, this is an aqueous reaction. This reaction is taking place in solution. So not only are there a bunch of silver ions and chloride ions floating around, but there's a whole lot of what floating around as well? In a solution. How did I create this aqueous solution? Water. In fact, there's way more water molecules floating around than there are silver ions or chloride ions, right? A solution is vast majority water molecules, right? All right, so first of all, how much heat was absorbed or released by our solution? We got to use that conservation principle. The fact that however much heat is absorbed or released by our reaction plus that of our solution, they have to equal 0. All right, that negative 16.425, which one was that? Our Q reaction or our Q solution? That's our reaction, right? That's considering how much, if we consume this much silver, how much heat will be released. So that's our reaction right there. So that plus our solution has to equal 0. So then what is our Q solution? Positive 16 point whatever. Oh no, sorry, not per mole, just kilojoules. All right, and again, I can keep my sig fig marked here. So then did my solution absorb or release heat? It absorbed heat. Where did that heat come from? That was the heat that was released by that chemical reaction, right? So those silver ions combine with those chloride ions, and when they form that solid silver chloride, they release heat. Where does that heat go? It goes into that surrounding solution. All right? So now we can take this one step further here using our calorimetry equation. So let's say if our solution has a mass of 1,200 grams, what is the observed temperature change? We're talking about heat. We're talking about temperature change. What equation are we going to need to use? We're rewinding all the way back to that discussion of calorimetry, right? So now we're going to use our Q equals HC times M times delta T. All right, so in this equation here, what Q am I going to use? My Q of my solution, right? This is now my solution that's absorbed all that heat. All right, we have to be told how much of our solution we have, and in this case, it was given to us in our problem. Right? This will vary depending on whether you're carrying out this reaction in a little beaker or rather a little calorimeter or a big calorimeter. Exactly how much solution you have will impact the observed temperature change. And we're solving for what in this equation here? This is what we need to find. All right, so check. We have a Q, we have a mass, we need that delta T, but we're missing one too many variables here. That heat capacity. All right, remember that heat capacity is a constant value. Since we're talking about a solution, and we said that that solution consists of mostly what? Water molecules. So what heat capacity are we going to use? We're going to go to our constants page and we're going to look up that heat capacity for water. All right? Our solution's heat capacity, truthfully, will be slightly different from that of water, but it's a dang good approximation to use water's heat capacity for any solution. All right? So for our heat capacity of our solution, we'll use that of water's. And water has a heat capacity of 4.184 joules per gram degree Celsius. All right, so let's plug everything in here to our equation. The Q of our solution, that's what we solved for. That was that positive 16 point something, 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 425. We're going to keep our sig fig marked. This is going to be equal to that heat capacity, 4.184, times the mass, which was given to me in my problem. That's that 1,200 grams, times our variable we're solving for, that delta T. All right, so now we just have to solve for that missing variable. Before we do that real quick, I want us all to pay attention to our units here. We have a units problem here. At the end of the day, what should I be left with units of if I'm solving for a delta T? I better be left with temperature units, right? Degrees Celsius. But I have two units that aren't going to cancel out with one another in this problem to leave me with our with just degrees Celsius. On the one side, I have my energy measured in kilojoules. And on the other side, my heat capacity is given to me in units of joules. Those aren't going to square away. Luckily, at the very beginning of the semester, we learned how to do these unit conversions. So we can convert from kilojoules to joules so that our units are all squared away at the end. All right? It actually doesn't matter which one you convert. You could convert your heat capacity into kilojoules per gram degree Celsius, or you can convert that heat into joules. As long as they match, you'll get the right answer. All right? I'm going to do my heat over here. My 16.425 kilojoules of heat. I'm going to multiply that by 1,000 because there are 1,000 joules in 1 kilojoule. All right, cool. So everybody take a second. Tell me what the delta T is for this reaction here. All right, we perform this precipitation reaction. Just how much is that going to heat up that surrounding solution? All right, so if we punch this all into our calculator, solving for that delta T, we get a delta T of 3.27139, and our units work out to be degrees Celsius, And then we were really good at keeping track of our sig figs, so we know that that heat only has 2 sig figs. And so that, along with our mass, will limit us to 2 sig figs in our answer here. Or we would expect to have this solution change by increasing 3.3 degrees Celsius. All right, so we're kind of rolling together what we learned first about calorimetry and then what we learned more recently about reaction enthalpy. All right, if we're given a reaction and given a chemical equation, we can find its delta H from our constants page, and we can use that. Then if we know how much reaction is occurring, we can figure out how much heat is absorbed or released. All that heat needs to go into that surrounding solution. So now I can figure out the Q of my solution, and then finally turn that into a temperature change using our calorimetry formula here. All right, so now we're going to go the other direction. Given information about our temperature change, how can we figure out what the enthalpy of our reaction is, right? So we just did this problem go in one direction. Now we're going to go the reverse direction here. All right, so we're going to say now we don't know what this reaction is. An unknown precipitation reaction. All right, we're going to carry out this reaction, and it's a precipitation reaction, and we are going to have a total of 550 grams of our solution. All right, this decreases the temperature of this solution by 2.3 degrees Celsius when I carry out this precipitation reaction. All right, so step 1, tell me what the Q of that solution is. All right, once we have that Q solution, we can figure out the amount of heat that was absorbed or released by our reaction. All right, so using that calorimetry formula, tell me what the Q of our solution is. All right, so our Q solution is equal to the heat capacity of that solution times the mass of the solution times the change in temperature of that solution. What is the heat capacity of this solution? What are we going to look up on our constants page? Water, because every solution is vast majority water molecules. So that would be that same 4.184 joules per gram degrees Celsius multiplied by that mass of 550 grams. All right, and what is my delta T in this reaction? All right, my temperature change is 2.3 degrees, but importantly, this was decreasing by 2.3 degrees. So in my equation here, I need negative 2.3 degrees Celsius. That will give me a negative Q, which checks out. If a solution is decreasing in temperature, it had to release heat in order to do it. All right, so that means I get negative 5,292.76. My sig figs, I'm limited by this change in temperature here, so I have 2 sig figs. And then finally, what are my units here? Yeah, so grams cancel out, degrees Celsius cancel out, and I'm left with units of joules. You see that in certain contexts we use joules, and in other contexts we use kilojoules. It's going to be really important to pay attention to your units in this particular chapter so we don't get them mixed up. All right, great. So now I have my Q solution. How am I supposed to find my reaction heat here? Because they sum to 0. So exactly, I'm just going to flip that sign. My reaction, where did that heat go? If it was absorbed by my, if it was released by my solution, it had to have been absorbed by the reaction. So positive 5,292.76 joules. So then was this reaction endothermic or exothermic? Right? My solution released the heat, but that heat was absorbed by that reaction. So this would be an endothermic reaction. Again, endothermic reactions are what decrease temperature of the surroundings. If you perform an endothermic reaction, you feel your solution getting colder. All right, so then lastly, last thing I can ask you is say something like, if 0.50 moles of reaction occurred, what is the delta H of our reaction? All right, so that delta H of our reaction is just simply the amount of heat that's released by the reaction, but specifically per mole reaction. So from my calorimetry experiment here, I know that when this precipitation occurred, it absorbed that 5,292 joules. And now I'm being told that it was 0.50 moles of that reaction that actually occurred. So then I can figure out my delta H of my reaction by taking my joules divided by my moles. All right, and I get 10,585.52. All right, I'm going to round that to 2 sig figs. What are my units here of my answer? Joules, do these moles reaction cancel out? No, so then I'm just left with my delta H values, our normal delta H values of energy per mole reaction. All right, typically delta H values, if we look on our constants page, they're expressed in kilojoules per mole. We can see why, because they tend to be big numbers here. So it'd be more convenient to represent this as simply 11 kilojoules per mole reaction, rounding to my correct number of sig figs. right? This would be 11,000 joules per mole reaction. So then I just converted from joules to kilojoules to make it a more manageable looking number. All right, and again, that's how you will typically see delta H is represented when we use our constants page or our bond dissociation energy. We're always working in kilojoules per mole for our enthalpy. That is the typical units. All right, cool. So we have this relationship. We talked first about calorimetry in this class and how that relates to the change in temperature that you observe when heat is either absorbed or released. And then we talked about enthalpy, which is what happens when a chemical reaction absorbs or releases heat. And now we rolled them all together and we said, all right, let's say that we have a chemical reaction and that chemical reaction releases heat. Well, where does that heat go? All of that heat has to go into the surrounding solution. So then we can measure, or rather calculate, the change in temperature that we would expect given that amount of heat absorbed or released, going back to that calorimetry formula. All right, so we're kind of tying in the beginning part of this lecture with the end here. All right, cool. So again, next class we'll do review in preparation for exam 4. Actually, the next 2 classes will be review. Monday's review will be optional.